Okay, in this section, we will consider several linear dynamical systems in which the model is a second-order linear differential equation with constant coefficients. So the first sort of category of problems we're going to see are spring mass systems. Okay, so to kind of bring in this topic, let's imagine we have a spring that's just hanging from a ceiling. And there's no mass attached. So it's just kind of dangling there. Well, this is exactly the length that the spring wants to be. So let's call that length L. Okay, so, well, now let's attach a mass to the spring. And if we do so, the spring will stand a little bit and settle in to an equilibrium position. So there's our L, the length that the spring wants to be, but now the mass is stretching it a little bit, say an amount S. All right, now since this is an equilibrium position, that means that the weight of this mass is perfectly balanced against the restoring force of the spring, right, which would be opposite. It would be in an upward direction. And this balance here is at the heart of the model we're going to build. So for this, we're going to need Hooke's law. All right, so Hooke's law says a spring exerts a restoring force, F, which is in the upward direction here, and that restoring force is proportional to the amount of elongation S, right? So if S is equal to 0, then the spring's not exerting any restoring force, right? But if we pull the mass down farther, then there's going to be a larger restoring force, and it's proportional to the amount that we pulled down. So in this equilibrium position, the forces are perfectly balanced, right? So we have the restoring force this way, which we can see is proportional to the length S, so we'll call this Ks. And we have the weight of the mass, which we'll call W. And remember, W here is the weight. So that's really the mass times the acceleration due to gravity. So when the spring's in equilibrium, the weight is equal to Ks, or we could say weight minus Ks is equal to 0 as sort of the sum of the forces. Or you could write this, of course, as mg minus Ks is equal to 0. Okay, that's all well and good, but it's not very interesting to just look at a static spring in equilibrium position. What we'd really like to do is build a model that tracks the position of the mass over time. If we were to, say, pull down on the mass or even push it up a little bit and then let go, what would happen is the spring, of course, would extend and then shrink and then extend and then shrink and so on, and we kind of get this mass doinging up and down, and we would expect such a model ultimately to involve harmonic functions like sine or cosine. Okay, well, we have everything we need with our knowledge of differential equations and Hooke's law here in order to produce the differential equation, solve it, and actually get a satisfying result. Our model will not only account for having pulled the mass to a different location and letting go, but even giving it an initial velocity if we wish. So pulling the mass down and then giving it a little shove in either direction. All right, so let's paste in our diagram so far. And let's draw one more representing the moving mass. So again, this would be the equilibrium position with the mass. So we can call this length here L plus S. And then at this particular moment, there's an additional offset of x units. And again, the positive direction is downward. So this mass is sort of swinging up and down this way. And we've taken one quick shot of one frame here, and that's our x. What we want is x as a function of t. Yeah, you can imagine that this is going to be some sort of wave. All right, well, the mass will be accelerating when the net force is not zero. So let's track the net force on the mass in motion here. Let's call it F. Let's decree that F is a downward force, meaning positive values of F are downward. So what's contributing to F? Well, the weight of the mass, of course. But what about the restoring force? We need to subtract that. That would be proportional to the elongation of the spring. In which case, here, we can see that it's S and then plus an additional X. This K is referred to as the spring constant, and it depends on the properties of the spring itself, right? You can imagine that, of course, some springs are just stronger than other ones, and so on. Well, that information's wrapped up in the K here. And then our S plus X is how far the spring has stretched from its unstretched position of merely L. Okay, well, this can be written simply by distributing that negative K. We get force is equal to the weight minus Ks minus Kx. But we saw earlier that W minus Ks is equal to 0. So we actually simply have F is equal to negative Kx. And we're very close to our differential equation. We just need a way of writing F in terms of x. Well, let's recall Newton's second law. The net force acting on a body is equal to the mass of that body multiplied by that body's acceleration, which we'll write as the second derivative of x. Okay, so combining these two equations, we have the net force, which is m times d squared x over dt squared, is equal to negative kx. All right, this is starting to look like a differential equation. I mean, it is a differential equation. It's a second order as well, so it fits right in here in chapter 5. So let's move everything over to one side, as we tend to do for these higher orders. How convenient, it's homogeneous. And typically, we actually divide by m to get this thing in standard form. Okay, so this would be the differential equation that solving for x would give us an actual model describing this oscillating mass. So I will write this in one more form, which is fairly common. And that is to replace k over m with omega squared. So omega squared is, of course, just equal to k over m. But this makes actually solving the differential equation a little bit easier, and then we can refer to the omega as needed, or even work out the details, since we know that omega squared is always k over m. So yeah, let's solve this differential equation. Well, this is a homogeneous equation. So we get the auxiliary equation, m squared plus omega squared is equal to 0. And solving for m, we're going to get m is equal to plus or minus I omega. Well, this leads us straight to our final answer. X is equal to e to the, well, alpha here would be 0, so we'd go like e to the 0t, but that's just 1, times c1 cosine of omega t plus c2 sine of omega t. All right, so there's our model. And it's what we would have predicted, isn't it? With the oscillation, of course, giving us a function in terms of sines and cosines. So the oscillation has a period. And we know from trigonometry that the period would be 2 pi divided by omega. You can predict the period because you can calculate omega just if you know the spring constant and the mass. So you don't even need to solve the whole differential equation to learn the period of motion. All right, well, let's look at an example. Okay, so in this problem, we're given some information about stuff and asked to solve some stuff. So specifically, this mass weighing 4 pounds stretches a spring 18 inches. So they're talking about the equilibrium position for that particular mass. But obviously the rest of this is describing the actual situation where we've pulled the mass down a couple of feet and then not only let go, but gave it a little bit of a upward velocity of 2 feet per second. And of course, this thing is going to go doinging up and down. And like the scientists we are, we want to know the equation of motion. So yeah, you can, if you wish, start with the actual differential equation and then solve it. Well, let's start with, the model that we have just figured out. All we really need to figure out is what omega is, as well as what the specific constants are. All right, well, let's just figure these things out. So let's start with omega. Well, we know that omega squared is k over m. So we just need k and m. Once we've got k and m, we'll have omega. So I guess this is a sub-problem of finding k. Well, the mass weighing 4 pounds, stretching a spring 18 inches, that's the information we need to use Hooke's law in order to find k. So in equilibrium, the weight of the mass is equal to k times s. I'm using a very obvious capital W here for weight so that I don't mix it up with omega. So the weight was given as 4 pounds, and k is what we don't know, and s is 18 inches. Now, when you're working with this US system, it's better to use feet instead of inches. So let's convert 18 inches to feet, which is 3/2 of a foot. All right, you don't have to convert to feet. You can leave it as inches, but make sure that you include the units in your calculations so that if at some point later you have a combination of feet and inches in the same equation, then it becomes clear that one needs to convert over to the other. So we're solving for k. So we can see that k is equal to 4 pounds divided by 3/2 of a foot. So this evaluates to 8 over 3 pounds per foot. All right, we also need to find m. So we know that the weight is equal to m times g. So here m will equal to the weight divided by g. And the weight, of course, being 4 pounds. And g being 32 feet per second squared. Again, in the US system. In the metric system, of course, it's 9.8 meters per second squared. So this gives 1/8 of a pound second squared per foot. Now, this unit, and in fact your book goes ahead and just calls it that, this is one slug by definition, a pound second squared per foot. We don't need to use the word slug, but you can if you want. Your book does at that moment. I personally just always leave it this way. That way, again, if we encounter something in inches later, we can remember, we need to convert feet to inches or vice versa. Okay, so we have our k and we have our m, so we can finally find omega. This seems like a good spot for the greatest word in all of English language. Indeed, omega squared is k over m, and k is 8/3 pounds per feet, and m is 1 over 8 pounds seconds squared per feet. So what are we going to get here? So here we're going to get 64 over 3. And let's see what cancels unit-wise. The pounds cancel, the per feet cancel with per feet. And so our omega is 64/3 per second squared, right? So, okay, then omega is the square root of that. 8 over rad 3 per second. All right. So recall this is the form of our x, c1 cosine of omega t plus c2 sine of omega t. And so we know that it's now c1 cosine of 8t over rad 3 plus c2 sine of 8t over rad 3. So all we have to do is figure out our c1 and c2, and then we're good to go. Okay, but that's what the initial conditions are for, right? This is technically an initial value problem. The fact that we're told at t equals 0, the mass is released from a point 24 inches below the equilibrium position tells us that x of 0 is equal to 24 inches. Let's write it as 2 feet because our units are just going to be in feet. And we're given an upward velocity of 2 feet per second. Well, that tells us that x prime of 0 is equal to -2 feet per second. So if we plug those into our equation, we're going to get our c1 and c2. Okay, well, we're going to need the first derivative. So why don't we quickly write that down? So the first derivative is -8 over rad 3 c1 sine 8t over rad 3 plus 8 over rad 3 c2 cosine 8t over rad 3. So we're certainly going to need that for our second initial condition, but we don't need it for the first one. Let's plug the first one in. So we get an x value of 2 when we have a t value of 0. Okay, lovely. That's of course equal to 0 there. And really, this part here evaluates to 1. It's cosine of 0. So we can see right away that c1 is equal to 2. Okay, so now we'll use the first derivative to find c2 using this particular input. So we know that the first derivative is equal to -2 when t is equal to 0. Okay. We also know that c1 is equal to 2. So instead of writing -8 over rad 3 c1, we could write -16 over rad 3 sine of 8 times 0 over rad 3. That term's going to 0 anyway. Plus 8 over rad 3 c2, which is still unknown, cosine of 8 times 0 over rad 3. So that first whole term is 0. This, of course, evaluates to 1. So we get -2 is equal to 8 over rad 3 c2. And thus c2 is equal to -2 rad 3 over 8. That's just negative rad 3 over 4. Okay, so we're finally going to get our function. Here I've pasted in where we've left off. And we can now say x, which is of course a function of t, is equal to c1. Well, that was 2 cosine of 8t over rad 3 plus c2. Well, that's minus rad 3 over 4 sine of 8t over rad 3. And that is tracking our oscillating mass. Let's quickly find the period. Well, the period, which is often given by capital T, is 2 pi divided by omega. So that would be 2 pi divided by our omega. Now omega was 8 over rad 3 per second. So cleaning up this fraction, we're going to get rad 3 pi over 4, and we were dividing by per second, which means this is actually literally in seconds. So that makes sense for a period, something in seconds. It's always satisfying when the dimensions work out the way they should. Okay, why don't we check on Desmos this particular model, see what we get. To make Desmos happy, we should use y in terms of x. All right, so here we have our oscillating spring. Now remember, up on the y-axis here really means extending downward. So even though we pulled the thing 2 feet down initially, right, 24 inches down, it's showing here as a y-intercept of positive 2. Okay, so the spring's kind of upside down at this point. So we also gave it an upward velocity of 2 feet per second. What that means is if we want to confirm this, we can graph a straight line here and just see if it's tangent right there. And we'll give it a slope of -2, which would be representing that upward velocity. And we'll give it the y-intercept of 2. And let's confirm that that's really tangential. And it is. So yeah, this really seems to be representing our model here. So that's cool. Okay, so that's super cool. We're the masters of, tracking oscillating springs now. But we're not really tapping into the true power of differential equations here. I mean, we definitely are, don't get me wrong. But we're missing something. For instance, this is a pretty low resolution model, right? Like we know in real life, if we let go of a spring, it's going to bounce up and down for a little while, but it's going to slowly work its way back to the equilibrium position and then not move at all, right? So we're not accounting at all for, say, air resistance. And we can, right? We're empowered to do that because we understand how to take additional information and incorporate it into our differential equation and produce a brand new model out of that. So yeah, let's account for air resistance. Okay, well let's jump back over to this formula here. Except this time we have an additional constraint on our net force, which is subtracting, and we'll call it beta times the current velocity. So remember, the F here is mass times the second derivative of x with respect to t. And let's move these other guys over. So we'll add the beta times v, but the instantaneous velocity, let's not write it as v, let's write it as dx dt. And then we'll move our kx over, and we've got our 0. So if we account for air resistance, that's just bringing in this middle term here with the first derivative. Let's see an example. Okay, so once again, we have a spring with a mass, and this time we've come along and pushed the mass up along the spring 2 feet above its equilibrium position, and then we just let go. So this time it has no initial velocity, at least, except it's going to doing downward and upward and downward again, and so on. But we also have some air resistance, or whatever sludge resist. I mean, it's in something, surrounding medium, and it's not very specific. So we might be doing this in mud. But let's, figure out the model, right? So we want x of t. So let's start with, we know that m times the second derivative of x plus beta times the first derivative of x plus kx is equal to 0. So yeah, we need our m beta, and k. And remember, once we've solved the differential equation, we're going to have C1 and C2, which we'll use the initial values to determine. So it may not be clear right away which ones are initial values and which ones are information about the system, but we will figure that out as needed. So we need M. That's certainly information about the system. So let's find M. So the weight is 16 pounds. And so the mass would be the weight divided by G. So that would be 16 pounds divided by 32 feet per second squared. So that means that the mass is 1/2 of a slug, right? Or we'll say pounds second squared per foot. So 1/2 of a slug. All right. Now let's find beta. Well, beta is the constant of proportionality with respect to the resistance of the surrounding medium relative to the instantaneous velocity. Here it says that the surrounding medium offers resistance numerically equal to the instantaneous velocity. So that tells us that this constant of proportionality is equal to simply 1. And finally, we need to find k. All right, well, k is the spring constant, and this first sentence here tells us how to find it, because normally the spring would be 5 feet long, but as soon as we hang the mass on it, it's 8.2 feet long. So we know that weight is equal to k times s, and the weight is 16 pounds. K is what we're after, and s is the elongation of the spring, so that would be 8.2 minus 5 feet. So k would be 16 pounds divided by 3.2 feet. That would, of course, be exactly 5 pounds per foot. All right, so the differential equation is given as follows. The mass was 1/2, beta was equal to 1, and our k is 5. So if we double everything, make life a little bit easier, we'd get x double prime plus 2x prime plus 10x is equal to 0. Okay, so let's just solve this. Hooray! It's a homogeneous linear differential equation. So let's just write down its auxiliary equation. I don't think this is going to factor. So let's use the quadratic formula. So we get -1 plus or minus 3i. Okay, so then our solution is e to the -1 times t, c1 cosine of 3t plus c2 sine of 3t. So all we have to do now is determine what c1 and c2 are. Okay, so the mass was released from rest 2 feet above the equilibrium position. That means at time 0, the position was -2. And being released from rest means that the first derivative at time 0 is equal to 0. The velocity at 0 was 0. So very good. We're going to need the first derivative. Let's worry about that in a minute, though. Let's just plug in this point right here. So we have -2 is equal to e to the -0. Of course, that's just going to be 1. c1 times cosine of 3 times 0 plus c2 sine of 3 times 0. So that's 0, and what we get is just -2 equals c1. Okay, that's very nice. Okay, so now let's use the first derivative at 0 equaling 0. Of course, we're going to need the first derivative. So x prime is, okay, wonderful. We're going to need the product rule. So derivative of e to the -t times this stuff. We know that c1 is equal to -2, so we can just put that in directly. And this is plus, because we're in the middle of a product rule, e to the -t times the derivative of this stuff. So derivative of cosine is, of course, negative sine. The 3 comes out. 3 times 2, that'll be 6 sine of 3t. And then plus 3c2 cosine of 3t. Okay, so we're plugging in 0 for x. We get 0 for x prime. So, of course, these e to the stuffs, those will just be 1. Let's write it in anyway, just to make sure we don't make any mistakes. Cosine of 0, sine of 0, sine of 0, cosine of 0. Okay, so these guys are dead for sure. So what we have is 0 equaling -1 times -2 plus 1 times 3c2. So here we get c2 is equal to -2/3. All right, so our final answer is that x of t, or x, is equal to e to the -t times c1, which was -2 cosine of 3t minus 2/3 sine of 3t. Okay, let's see what that behavior looks like on Desmos. Okay, this is very descriptive of the situation. We have the oscillating motion, but clearly it's being dampened by the air resistance until it's not perceptible anymore. Are the initial conditions represented? So here clearly we have a y-intercept of -2, which means, of course, that time equals 0. Our elongation's at -2, right? Because it was pulled up above the equilibrium position by 2 feet. Also, you can see that the curve has a critical point right there. Of course, that's a local min, and that's because the derivative at that point is equal to 0, as there was no initial velocity given. It was just let go of. So, yeah, math seems to work, doesn't it? Okay, so recall from section 1.3, we talked about LRC-Series circuits as a model of differential equations. And we produced a second-order differential equation. But of course, way back then, we didn't know how to solve even first orders. That's not a problem anymore. So yeah, let's revisit LRC-Series circuits. Okay, so the situation was we had a circuit with an inductor, a resistor, and a capacitor. And by Kirchhoff's second law, the sum of the voltages equals the voltage impressed on the circuit. All right, and the voltage through the inductor is the inductance multiplied by the rate of change of the current. And remember, current is I. The voltage through the resistor is the resistance times the current. And the voltage through the capacitor is 1 over the capacitance times the charge. And that equals the impressed voltage. So the inductance is measured in henries, the resistance in ohms, and the capacitance in farads. So I was the current, and Q is the charge. And the key here is that the current is the rate of change of charge. So that allows us to actually write this differential equation purely in terms of charge, and we're going to get a second order differential equation. So we're going to get the inductance times, instead of di dt, we'll write that as the second derivative of charge, plus resistance times Instead of I, we'll write that as the first derivative of charge. And 1 over the capacitance times charge. Okay, so clearly we have a differential equation. And let's look at a specific example where we have given information. Okay, so here we're going to find the charge, meaning we're going to solve the differential equation with the following given information. The inductance is 0.25 henries, resistance is 10 ohms, the capacitance is 1,000th of a farad, and we have an initial charge as well as Q prime, which is of course current here. So yeah, I had this exact problem at Ralph's the other day trying to buy bananas. So let's solve it. Of course, we're going to use this formula here. So our L is 0.25 henries. Let's write that as 1/4. The resistance, 10 ohms. The capacitance is 1,000th of a farad. So 1 over C, that would actually be simply 1,000. And E of t is 0. It's probably going to be slightly easier to write this in standard form, so let's just multiply everything by 4. So we have this here, plus 40 dq dt, plus 4,000 q equals 0. So yeah, it's a homogeneous second order linear differential equation with constant coefficients. That's right in our wheelhouse. So let's solve this thing. Of course, we're going to need the auxiliary equation. And because this equation is a jerk, it does not factor. So we'll use the quadratic formula. Okay, so m is equal to negative b squared minus 4 times a times c all over 2 times a. All right, well, we can certainly factor 40 out of that. What does that give us? 40 minus 400. We can factor another 40. Okay, so this is like negative 20 plus or minus 20 times 3i. So that's negative 20 plus or minus 60i. Okay, so those are our two complex conjugate m values, which means that the solution is going to be q of t equals e to the negative 20t, and then c1 cosine of 60t plus c2 sine of 60t. Very good. So all we have to do is use the initial values that were given in order to figure out what c1 and c2 are. So we were given the initial values. Q of 0 is Q naught, and I of 0 is equal to 0. And remember, that's just like Q prime of 0. Okay, so let's plug in Q of 0 equaling Q naught. So Q naught is e to the negative 20 times 0, c1 cosine of 60 times 0, plus c2 sine of 60 times 0. So that guy goes to 0. This guy here is 1. This guy is 1. So we just get that c1 is Q naught. And now we need to find Q prime in order to plug in the other initial value. So Q prime of t is derivative of e to the negative 20t, which is negative 20 e to the negative 20t, times this thing. C1 we know is Q naught. And plus, because we're in the middle of the product rule, e to the negative 20t times the derivative of that thing. So that would be negative 60 Q naught sine 60t plus 60 C2 cosine 60t. And So setting q prime equal to 0 and t equal to 0, we get negative 20 times q naught plus 60 C2. Again, we've seen this pattern before. All the sines are going to go away, and all the cosines will just become 1. And even e to the stuff times 0 will just be 1. So we just have to solve this equation for C2. So 20 q naught is equal to 60 C2. So C2 is 1/3 q naught. And therefore, our final answer is that q, or q of t if you wish, is equal to e to the negative 20t q naught cosine of 60t plus 1/3 q naught sine of 60t. We should pull that q naught out, so whoever's working with this equation isn't burdened with plugging it in two places. That's much nicer, isn't it? So there's our final answer.